Imagine you're standing on the bridge of the largest moving object ever built by human hands. You look out ahead and see the harbor entrance. The port is close, maybe 10 kilometers away, and then the captain gives the order, full stop. The engines begin to slow, the propeller stops turning, and the ship keeps moving. It keeps moving for the next 8 kilometers. At no point does it stop quickly. At no point can anyone force it to. The only thing left is physics, and physics doesn't negotiate. This is not a malfunction. This is not an emergency. This is exactly how a supertanker stops under normal conditions. And most people have no idea that a vessel this large operates under rules that have almost nothing in common with anything we drive, ride, or fly. We understand stopping intuitively. You press the brake. Friction converts kinetic energy into heat. The object slows. It works for bicycles, cars, trains, even aircraft, despite weighing hundreds of tons, stop within roughly 2 kilometers using layered braking systems. So when we first hear that a supertanker needs 8 kilometers to come to a halt, most people assume the ship simply has inadequate braking. They imagine that if engineers just built better systems, the stopping distance could be dramatically reduced. That assumption is wrong, and understanding why it's wrong requires rethinking what stopping actually means at this scale. The problem isn't the braking system. The problem is the sheer quantity of energy that needs to be dissipated and the fundamental physical limits of how quickly that can happen. Let's put the numbers into perspective, because they are genuinely difficult to absorb. A fully loaded VLCC, a very large crude carrier, has a displacement of around 300,000 to 320,000 metric tons. For reference, the Eiffel Tower weighs approximately 7,300 tons. We are talking about a ship that outweighs the Eiffel Tower by a factor of more than 40. Its length is typically around 330 meters, roughly the height of the Empire State Building laid on its side. When this vessel is moving at cruising speed, which is typically between 14 and 16 knots, approximately 26 to 30 kilometers per hour, the kinetic energy stored in that moving mass is colossal. Kinetic energy scales with the square of velocity and linearly with mass. At 15 knots, a 300,000-ton tanker carries roughly 900 megajoules of kinetic energy. That is equivalent to the explosive energy of approximately 215 tons of TNT. You cannot dissipate that energy quickly without either destroying the ship or violating the laws of thermodynamics. The stopping sequence for a fully loaded supertanker under normal conditions takes approximately 14 to 20 minutes from the time the engines are reversed to the moment the ship comes to rest. The distance covered during that time is between 7 and 10 kilometers, depending on the vessel, load, sea conditions, and method used. Even in an emergency stop, where the engines are immediately thrown into full reverse, the ship will still travel between 3 and 5 kilometers before halting. There is no such thing as a quick stop at this scale. Most people, when they first learn this, ask the same question: why not just install stronger brakes? The answer is that ships don't have brakes in the conventional sense, and if they did, it wouldn't help. In a car or airplane, a braking surface applies friction to rotating components, wheels, discs, and the vehicle's kinetic energy is converted into heat through that contact. On a ship, there is no such surface. The propeller is connected to the hull through water. Water is not a rigid medium. You cannot apply a clamping force to it. The only way to slow a ship is to reverse the thrust direction, to use the propeller to push water forward instead of backward, or to use the ship's drag through the water itself. Drag increases with the square of speed. The faster the vessel moves, the more resistance it encounters. But at the low speeds a supertanker operates, drag is not a powerful enough force to stop the vessel in a short distance. There is a second misconception worth addressing here. Many people assume that a ship's anchor is used for emergency stopping. It is not. Dropping an anchor at speed would place catastrophic loads on the chain and the anchor mounting points. The forces involved would destroy the anchor system. Anchors are designed to hold a stationary or nearly stationary vessel in position against wind and current, not to arrest a moving 300,000-ton mass. Using an anchor as a brake is not an engineering limitation that hasn't been solved. It's a physical impossibility at this scale and speed. So how does a supertanker actually stop? The process involves 3 primary mechanisms: and they work in a specific sequence. The first mechanism is engine deceleration. A VLCC is powered by a two-stroke low-speed diesel engine, typically a single engine driving a single large propeller. These engines are among the largest reciprocating machines ever built. The MAN-B and W12S90ME-C, for instance, produces around 68,000 kilowatts and turns at approximately 94 revolutions per minute. When the order to stop is given, the engine's fuel injection is cut. Without fuel, the engine decelerates, but the propeller is still being turned by the inertia of the ship itself, acting through the shaft. The ship's forward momentum is so large that it physically drives the propeller. This is called propeller windmilling, and it generates some resistance, but the effect is relatively small compared to the total energy in the system. The second mechanism is thrust reversal. On most large ships, the propeller cannot change its blade pitch while rotating, unlike aircraft propellers or some smaller vessels. To reverse thrust, the engine must be brought to a near stop, then restarted in the opposite rotational direction. This process takes several minutes on a large two-stroke diesel. Once the engine is running in reverse, the propeller pushes water forward, generating a braking force. But this force is limited by the power of the engine, the efficiency of the propeller in reverse, and the speed of the water flow. In reverse, propellers are significantly less efficient than in forward operation, roughly 60 to 70% less effective per revolution. So even at full reverse power, the braking force is considerably lower than the forward propulsive force. The third mechanism is hydrodynamic drag. As the ship slows, water resistance acts continuously on the hull. This force is proportional to velocity squared. It is strongest when the ship is moving fastest and diminishes rapidly as speed decreases. In the final stages of the stop, when the ship is barely moving, drag contributes almost nothing. The ship must rely entirely on the reversed propeller thrust to arrest the last residual motion. There is a deeper engineering logic here that explains why the stopping distance cannot simply be reduced by building a more powerful engine. The constraint is not power output, it is energy budget. All of the kinetic energy in the moving ship must go somewhere. In a car, it goes into heat at the brake pads. In an aircraft, it goes into heat at the brakes and into thrust reversal. In a ship, it must go into the water. The reversed propeller accelerates water forward, imparting momentum to that water mass. The energy transferred to the water comes directly from the ship's kinetic energy. But water has a fixed density of approximately 1,025 kilograms per cubic meter. The propeller can only move so much water per second. To double the braking force, you would need to move water at 4 times the rate, because momentum transfer scales with the square of propeller speed in reverse. This means that increasing engine power yields diminishing returns in stopping performance. A propeller 10 times more powerful would not produce a 10 times shorter stopping distance. The physics of momentum transfer in water creates an inherent ceiling. There is also a structural argument. The forces involved in reverse thrust on a supertanker are already enormous. The propeller shaft, thrust bearings, and hull mounting points must absorb all of the reverse braking force. Designing these components to handle even greater loads for the sake of reducing stopping distance by a fraction would add massive weight and cost for minimal operational benefit. Naval architects have long concluded that the optimal solution is not a more powerful stop, but a more carefully managed approach. Planning the deceleration sequence kilometers in advance is the engineering answer to a physics problem that cannot be solved by brute force. This physics is not just an academic curiosity. It directly shapes how supertankers are operated in practice. In congested waters, narrow straits, and port approaches, tankers begin their deceleration procedures many kilometers before their destination. The Strait of Malacca, one of the busiest shipping lanes in the world, has maximum speed restrictions for large vessels precisely because the stopping distance at higher speeds creates unacceptable collision risk. Pilots, specialist navigators who board ships to guide them into port, must calculate stopping sequences before they even step aboard. They account for the vessel's current displacement, the sea temperature and salinity which affect hull drag, tidal currents, and wind. A miscalculation of even a fraction of a knot in approach speed can add hundreds of meters to the stopping distance. In many major ports, the approach channel is specifically engineered with the supertanker's stopping distance in mind. Emergency anchorage areas are placed at calculated distances from the harbor entrance. Tugboats are stationed not as a courtesy, but as a functional component of the docking system, providing braking and steering force that the ship itself cannot generate at low speed. The tugs effectively act as external braking systems for the final phase of docking, where the ship's own propeller has become too inefficient to control precisely. Modern supertankers are also equipped with bow thrusters, transverse propulsion units mounted in tunnels through the bow, but these are primarily for lateral positioning at very low speeds. They contribute essentially nothing to longitudinal deceleration. What happens when a supertanker cannot stop in time? The consequences depend entirely on what it cannot avoid. In open water, a ship that has misjudged its stopping distance will simply overshoot its intended stopping point. Inconvenient, but not necessarily catastrophic. In confined waters, the outcome can be severe. The grounding of the Exxon Valdez in Prince William Sound in 1989 involved a vessel that demonstrated exactly how unforgiving the physics of large vessel maneuvering can be. A VLCC that strikes a reef, a sandbar, or another vessel at even low speed, 3 or 4 knots, delivers an impact equivalent to many thousands of tons of force. The structural consequences are severe. There is also the question of what happens in reverse thrust failure if the engine cannot be restarted in reverse. Due to mechanical failure, loss of compressed air for starting, or a seized crankshaft, the ship has effectively lost its primary braking mechanism. In this scenario, the only available option is deploying anchors as drag devices in shallow water, using tugs to apply external braking force, or accepting that the vessel will run aground in a controlled manner at the least harmful location available. Emergency procedures for exactly this scenario are part of every VLCC crew's training, precisely because the probability of engine reverse failure, while low, is not zero, and the consequences are too significant to leave unprepared. So when we return to that original question, why does a supertanker take 8 kilometers to stop? The answer is not a failure of engineering. It is the correct engineering response to an irreducible physical reality. You cannot stop 300,000 tons of moving mass quickly without somewhere to put the energy. There is no brake pad large enough, no anchor strong enough, no propeller powerful enough to short-circuit that equation. What maritime engineers have done is design systems that manage the stopping process as efficiently as physics allows, and train navigators to plan far enough ahead that the limitation never becomes a crisis. The ship doesn't stop slowly because nobody has solved the problem. It stops slowly because that is the only honest answer the laws of physics permit. And every kilometer of that deceleration sequence is a precisely calculated event, not a passive drift. The 8 kilometers is not a flaw in the design. It is the design. That raises one more question I haven't answered yet, and it's one that surprises almost everyone who hears it for the first time. If the anchor can't stop a moving supertanker, what exactly is an anchor chain designed to hold against? The forces involved and the engineering behind deepwater anchoring are far more counterintuitive than most people expect. I've covered that in detail in another video.